Hello class, I have presented my desktop. Okay, hopefully you can see it also. Okay, first welcome to our this session, but unfortunately I'm required to stay at home. Okay, so sorry for the inconvenience. Okay, the reason is I have a family member who uh, testing, who are not well, so see doctor. Nowadays, when you see doctor, they always ask you to do a test, lah. Okay, so I'm sure it will be nothing happen, lah. But in the meantime, everyone are required to stay at home first. So I'm also required to stay at home for these 2 days. So couldn't go and meet you, okay, in person. It's a bit difficult because I know you have lesson. You have lesson right after my tutorial, right? So it's not easy for you. So uh, we'll try lah. If you have a computer, you can log in to use your computer. If you don't have, okay, please log in using your handphone. Today, most time, I will be doing the talking. Okay, I will try to talk more so that you can to try to clarify the points and to show you the main ideas lah. Okay, so instead of you using your handphone to do using class point, I think now it's not so convenient lah. When we do online, you need two devices to listen as well as do the class point, right? So you need a computer to actually listen to my presentation, and you need a handphone to do class point. So I'll try not to do both. Okay, maybe at the end, the exit poll, we can turn on the class point, but for this session, mostly I think we'll just try to I just try to do the talking. I try to explain. Okay. So as you can see, this is our second week. In second week on our module website, we have placed some materials for you to go through. If you are not so sure, okay, here I can show you. So if you click on learning resources in our Blackboard, right, there are lectures. The lectures are here on week 1, 2, 3. We are now week 2, so you can go to week 2 lectures. There are multimedia materials developed for the for this lecture 2. Right, this is on programming PLC. Basically, this part we try to cover some foundations for PLC programming. All right, although we have done some programming. All right, but some basics maybe we can elaborate a little bit more today. Okay, so you go through these files which have voice recording, videos, and so on. All right, so and then after that we do tutorial. But to help you, I also have a PDF version, okay, which is also available on Blackboard on this roughly the main ideas. So for today's session, what I do is I will go through a few slides here to share with you on the main points of PLC programming, the requirements. And then after that, we have a quick look on the tutorial questions. So we have a few tutorial questions, tutorial 2 questions here. All right, we have a quick look on some of them, and if necessary to discuss, and we can have a quick look on that as well. Okay, so this is my plan. Mostly today, I will be doing the talking lah. Okay, so for first, we just have a quick look on the lecture notes on how to do programming. Now, after our first practical, you will notice that to do programming, actually we need to use the device, the PLC connections. When we have a PLC, the PLC have input-output connections. They have terminals. Some of the connections are on the PLC itself. Some of the connections may be on a remote I/O module. All right, but there will be terminals that can allow you to connect devices. These are called input-output devices, input-output terminals. So we can connect input devices to these terminals, to the input terminals. We can connect output devices to the output terminals. Right, do take note that when we say input device, output device, what is an input device? What is an output device? It's actually input device is one that provide the information to the PLC. For example, you measure temperature, and then the device, the temperature sensor, will send the temperature information to the PLC. So a temperature sensor is an input device. All right, or you can have a switch. All right, a switch is the user can press to close or open the switch, and the switch is connected to the input terminal of a PLC so that it provides information whether the switch is opened or closed to the PLC, and then the PLC will PLC program will take care on how to use the information, right? Output connection or output terminal is one that you connect to an output device. Output device are those devices that listen for instruction from the PLC. So in other words, they are devices that are controlled by our PLC. So we can, for example, it could be a motor. All right, we can instruct the motor to turn on, turn off, to run, or to stop. Or it could be a light that we can turn on the light, turn off the light. So those light, alarm, okay, motors, pumps, okay, these are devices are called output devices. The output devices are referencing to the PLC. That means to the PLC, they are output devices. They receive information from the PLC. All right. So all the PLCs will have some I/O connections for us to use. Now these I/O connections will be able to identify. On our Siemens PLC, okay, so there are terminals like this. So here you can make connections, right, to our devices. Now the devices, apart from digital input/output on/off devices, they can also be analog devices. That means there may be device that can send, let's say, the temperature sensor. All right, not only just turn on, turn off, but can actually send the signal that represent the temperature to the PLC. So these are called analog devices. So digital devices are DI/DO or DQ, right? DI digital input, DQ or DO are digital output. Analog devices are called AI or AO or AQ sometimes, right? AI is analog input, okay, and AO is analog output. All right. So before we do programming, by right, we must know the devices that is connected to our PLC, because we are going to use the information from devices to do the programming, right? We must know what is the sensor available to us and what is our output that we're supposed to program. Okay. So inside the PLC, the hardware configuration, we actually can see all these connections. In our last lab, we didn't do this, but next session maybe I'll show you. Okay. All right. Let's see whether anybody waiting. Okay. If still anybody trying to join in, please alert me. Maybe sometime I look at my PowerPoints, I cannot see the information on this side. So just alert me, I can admit them. Right, okay, so what I'm saying is inside our hardware configuration of the PLC, which we didn't really do in detail last session, we can specify who is connected where, okay? So inside the I/O connections, we can have a page like this inside the I/O module, and where you can see all the connections. These are the actual physical representation of all the I/O connections. And you can give a name, let's say this one. Okay, this one, %I 10.0, right? You can give a name, call it push button. And then in our program, okay, you can represent it by push button. You can still use %I 10.0, but you can also use a name push button. So in PLC programming, we normally would have a name, okay, because a name is a lot easier for us to use rather than these numbers. Imagine if you have hundreds of these numbers, well, very soon you won't know who is who, right? So, but if you give a name, temperature sensor, pressure, detector, okay, the alarm, LED one, and so on. So those will be easier for us to know what it is. All right. So the I/O physical devices connected would normally will give them a name. They are called a tag name. Right. This name we can give in many ways. So one way is in the configuration, hardware configuration itself, we can provide the names. Another one is like what we did in our practical. We can just use practical, and then we can just we can right click on the name and just define it and link it to the address, right? So that's what we did also. That's also okay, right? There are different ways we can give a tag name to these connections. All right, so our programming meaning that we are going to use these connection names, our addresses, to in our program elements, right? This is an example here. Okay, the LED example of the output. Okay, so it's okay, yeah. All right, so the way to program, I think now we already have a session. So let's see. Okay. The way we program, we already have some experience. So now you probably are easier for you to understand now. So when in our program, when we make a element, and we can right click to define this the name of the tag name, and when we define, we notice that actually different types we can associate a tag name to, right? Like it's a global input, a global output, our is a global memory, our is part of the data block. We haven't used data block, okay, but we have used global input, global output, and the global memory. Okay, so later we will also touch on data blocks, which not today, okay. So some other time when we start using them. So at the moment we have used global input, global output, and global memory. So these are items that we have tag names related to, and then we can do our programming using these tag names, right? So this is a basic idea. Right? So for the programming itself, the programming itself is relatively straightforward. Okay, we can have this ladder logic programming is the two end. Okay, you can imagine current flows through this one end to the other end. And if the conditions allow current to flow, the output will be activated. All right. So this is a basic idea. And the elements that we use are called contacts most of the time. Contacts, okay. And there are two types of contact. One is normally open, normally closed. Okay. Normally open, normally closed. Actually, this concept of normally open, normally closed can be confusing. Okay, some of you may not be so easy to understand this concept. Okay, this normally open, normally closed concept. All right, because the main thing is this: there are two types of normally open, normally closed. One is the device itself. Okay, let's say we connect a button or switch or button to our PLC, right? Like shown here, the start. Okay, this device itself can be normally open or normally closed, meaning that when you first connect this device to the PLC, if you by default it is open. Okay, it didn't activate the input, the corresponding input. So this is called a normally open device. But there are also devices when you connect to the PLC, you actually can make it already closed before you do anything, right? So among our practical rack, all right, we have a group of buttons. Actually, one of the button, the red button, is wired in normally closed format. So that means that red button on our when we are using our lab rack, the red button is already normally closed. So physically it's already normally closed. That means that button connected to our PLC, if you don't do anything, you already activate that input. So it's not normally closed. but all the other buttons is normally open. That means if you don't do anything, okay, it didn't activate the input. Now, when we use the program, when we start to do our program, inside our program, we can link or contact to a input. Like I use this contact to link to the start. All right. So when I link this normally open contact to the start, so it is normally open, right? So when the start is open, it is also open. But when I link the a switch, normally open switch to the stop connection, then it will be already closed. That means before you do anything, this is already activated. That means allow activity in the sense it allow current to flow. Okay, it allow current to flow. So there is this confusion now. You physically whether connected as a normally open or normally closed is you doesn't affect in your logically in your program. You can put it as a normally open, normally closed, right? So you have to know the combination. That means a normally open, this one, that is in my program, I program the start as a normally open contact here, right? I also need to know whether the physically it is normally open or not, right? In order to know whether current can flow through or not. Right, though this can cause a lot of confusions, in the beginning, especially, so some of you may not be so clear. At the moment, I think we try to understand the normally open one first. Okay, imagine, okay, a device is normally open, so you connect to our PLC, right? Unless it is activated, otherwise the input is not activated. And in our ladder diagram, if we use a normally open contact to represent this input, right? Then it tallies with a device. It tallies with a device. So at the moment, I think we just remember that one. So normally closed, we try to explain to you a bit more when we use them. Okay, yeah. Using the ladder logic, we can construct these logical operations, right? So this is a AND logic, where if you have two contacts connected in series, it means both have to be on in order for the output, this corresponding output, to turn on. So you require both to turn on. So in terms of the logical numbers, that means only when this switch 1 is 1, switch 2 is 1, then the output can be 1. Any other combination will be 0, okay, like this here. Okay, right here. Okay, so this is an AND logic. The AND logic is everyone must be on in order for the output to turn on. So this is a OR logic. The OR logic is any one of the input, okay, will turn on the output. All right. So you can see this is OR logic here. Any one of the input turn on, you make the output to turn on. Only when both turn off, the output will turn off. So this is called the OR relationship, right? So intuitively, we can see the way the current flow. So if imagine that current can flow from this side to this side. So if any one of the switch is closed, the current can flow through and turn on the output. So that's the idea. So that's our OR relationship. And OR is the most basic relationship. There can be also combinations, okay, like this one. Okay, this connection would mean that you have this normally open is in series with this normally closed, and this same one, switch 1, is normally closed, and this one normally open. So you connect. Okay, this one we can try to follow the logic. Okay, if you connect the ladder is programmed in this way, the output, okay, will behave like this. Okay, so when both switch 1 and switch 2 are on or off, the output will be off. Only when they are different, you see, this one either 0 or 1 or 1 0, then the output is on. This is called an exclusive OR. Okay, an exclusive OR is when there are two input, okay, the two input must be different in order to turn on the output. Right? If they are the same, they cannot turn on the output like this. Both 0 or both 1 cannot turn on the output. They have to be different in order to turn on the output. So this is called the exclusive OR logic. All right. When you program, then you can also have such relations. I mean, if you need to have such relations, you can program in this manner. Okay, someone is waiting. Okay, good. Okay, we get almost everyone in now. Okay, beside the exclusive OR, there is also an exclusive NOR, right? It's just the opposite of exclusive OR. Only when the inputs are the same, the output will turn on. And then when they are different, the output will turn off. Okay, right? There are applications, okay? There are cases we need to use this. So maybe later I share an example. So this is some explanation on the series of programming. Okay. Now what I do is we have a quick look on the tutorial questions. Okay, today we can ignore the class point now. Okay, so we just discuss on these questions. Okay, first is MCQ questions. So we have a quick look and see whether we need to elaborate or not. If not, no need to elaborate, we can quickly go through them. So it says the PLC engineer needs to understand what, such as sensors. So sensor is part of I/O device. Okay, so among the answers here are sensor belongs to I/O device, so it's an input device. So the choice here, the answer will be I/O devices, right? PLC engineers, okay, need to understand I/O devices such as sensors, right? So question 2 is PLC engineer need to know how to what the I/O device to the PLC modules. This is called interface or connect, right? As a PLC engineer, we will need to connect the devices to our PLC. So the connection is also called interfacing or interface. So this here is to interface the I/O devices to the PLC module. So we should choose B, the interface. Okay, question 3 is the PLC engineer needs to do what? Okay, here are a suitable PLC and an I/O module. All right, this one is the selection. Okay, a PLC engineer, okay, in the beginning, he needs to select a suitable PLC and I/O modules for his application. Okay, this one will elaborate more. Not right now. We don't need to say too much because there are quite a number of requirements when the engineer try to select suitable PLC and suitable I/O modules. There are quite a few considerations. Right now, we don't want to elaborate at this moment. We will have a chapter that will discuss more on the requirements. But right now, we just say, okay, this one is select D. Choice is D. Question 4. The PLC engineer would usually convert customers' requirement into something in order to provide clarity for programming. Okay, so this one not so clear, right? But let's try to decipher. You say the PLC engineer convert customers' requirement into something. That something will provide clarity for programming. So this is not programming yet, right? So it says the engineer will convert the customer's requirement into something, and that will help us to do programming because that it says provide clarity for programming. That means that something can make our programming a little bit more clear. Okay, so what is that? Okay, among these choices here are the correct one is C, flowchart. Okay, a flowchart is a good method that people often use, or the PLC engineer often use, to clarify how things work, right? So before we start our programming, it is quite common, okay, right? We change the requirement, the customer's requirement, into a flowchart. Okay, that means customer want us how to operate the the process. For example, if low level, okay, you open pump one, okay, until it goes to high level, then you close pump one and open pump two or something like that, right? So these are the user's requirement. So when we program our PLC, we follow such requirement. But it is a good way if we convert such requirement into a flowchart. And then when we do programming, we try to follow the flowchart. Actually, there is one type of programming called the sequential function chart. That is, the chart itself is a programming method. So we actually have a programming method that use directly the flowchart. Okay. In later part of our lab, we'll also introduce to you on that method. It's called sequential function chart. Now, but even if you want to do ladder programming, okay, we want to do ladder programming. We don't want to use sequential function chart programming. To have a sequential function chart in the beginning also helps us to do ladder programming. There is also a formal method. There is a method where how to convert a sequential function chart, okay, into a ladder program. We will also introduce to you on that one, okay? So although it's supposed to be in level 1, but I don't think we have time to do too much now, okay? So gradually we introduce all these concepts. Yeah, there is a formal method to convert flowchart into ladder diagram, right? So the conversion may not be the most efficient. That means you may not end up with a very efficient program, but it will work. It will work. Okay, now we have a look on the next question. Okay, class, just someone to tell me, are you okay? Because I'm not hearing you, so I cannot judge. Are you class okay? Your class? Just someone?
Can
Can, right? Okay, good. Okay, I just continue like in that case, Okay. All right. Okay. So this is question 5, MCQ. It says PLC engineer needs to do what? To the completed system, which will include testing, fine-tuning the PLC program to meet customers' requirements. Okay, this is elaborating that if you are the PLC engineer, in the end you complete everything, you still have to pass the whole system to your customer, and to make sure your customer are happy with the whole system. Now this process is called commissioning. Okay, it's called commissioning. So for this answer is actually A. So we commission our system, the completed system, and that's our to provide to our customer. Right? You may not be familiar with this word. Right? Commissioning is a industry word. Whenever you did something for the customer, you hand over your system to the customer. That process is called commissioning. So the commissioning will make sure you meet all the customer's requirements. All right, okay. Number 6 is how to assign the address prefix for the push button connected to the PLC. Okay, this one we should know. So we know that when we do programming, we can have tag names, and our tag names can be related to inputs, outputs, memory, our data block. So we have used input, output, and memory. We have not used data block yet. Okay, so we will ignore data block for the moment. But for a push button is an input device. A push button is an input device. Okay, if you want to configure the push button to link it to to an address, you have to link it to the input. So your push button's address will be something like %I something, right? So like we did our green button, right? It's called %I126.7. So that is a %I. So this answer would be A. It is %I. Okay, question 7. When would be the memory bit can be used? Okay, when do we use a memory in our programming? Well, actually, there's many cases, but we are given 4 choices, so we have a look at the 4 choices here and see which one is a suitable case for us to use the memory. So first one is when addressing the physical input output, physical input, which is wrong, okay? Because when we have actual physical input outputs, we use the %I or %Q, right? Then the second one, B, is when addressing PLC physical outputs. Of course, it's also not a physical one. Part C is when addressing logic without physical connection to input outputs. Yeah, so this looks more like it. So we just want to have some logic relationships without actually relating to the physical connections. This is the times we can use memory. Okay. The last one is when addressing input from remote IOs. No, even remote IOs also have physical addresses, so it's not memory. So the answer is C. So only when we are not dealing with not dealing with physical input output devices, then we can do we can use the memory. All right, this question, the question itself is wrong, okay? So it should not be this question. The question itself should be, what is this diagram, right? What is this logic? Okay, so ABCD, you link to this ladder. Okay, I mean in our lecturing slides, we actually have this. Is there anything? No. Okay, in our lecturing slide, we actually have this one. This is called exclusive hour relationship, right? So this will be C, okay? C, exclusive hour relationship. All right, now we have this design problem. Okay, it says design this ladder logic with this requirement. What are the requirements? 3 requirements. So first requirement is there is 3 pressure switches, PSW1, PSW2, PSW3. They are in normally open connections. All right, so normally is these are normally open. This condition, when all of them are closed, okay, then we may turn on the output. But they are not the only condition. We have another condition, which is I need 2 out of 3 door limit switches, LS1, LS2, LS3 are closed. Okay, and only 2 of them. We have 3 switches here, door switches. 2 of them must be closed. You know, then we may turn on the LED. All right, but this is not yet to turn on the LED because there is one final condition. Is there is a reset switch. Okay, the switch is also normally closed. Okay, and it is not activated. Only when the reset switch is not activated or not closed, all the 3 conditions together are okay, then the green LED will turn on. Okay, so this is a design problem. Okay, so I will go through this design with you to share with you on this. The next question. This is the next question. We will not do. Okay, let me see, do or not. We may do. Okay, let's see. We see whether we have time. Okay, let's have a look on the question 9 first. How do we actually approach a design problem, and how do we approach a design problem, and to accomplish the design with all the 3 requirements. Okay, so I will elaborate a little bit on this design philosophy. So I use this Microsoft Note to share with you how this can be done. So our requirement is like one main approach is like this. So we say there is these three requirements. We can actually do a three requirement to turn on the our output. Okay, so this is we have these three requirement here, right? The three requirement. One approach is to think about the three conditions and make the three conditions into three contexts. So we say the green LED will turn on when the three conditions are met. So I say this, for example, this is C1, C2, C3. So we call this, let's say I call these conditions. So C1, C2, C3 represent the three conditions. The three conditions will turn on our green LED. Okay, something like this. Okay, now this is one approach. I'm showing you one approach. So, but then we have the C1, C2, C3. They are all memory. Okay, they are all memory bits. They will represent the three conditions in the original requirement. So they will say all three pressure switches are closed. Only two of the door switches are closed, or the reset switch is not closed. So our design philosophy is like this. I will put the three conditions first, and then I will start program the three conditions. I'll program the C1 condition. C1 require all three pressure switches to be closed. So it's like this. There are three pressure sensors. They have to be closed in order for the condition 1 to be met. Okay, these are three switches. It's called PSW1, PSW2, PSW3. All right. So in order for us to show that, we can put a PSW1, PSW2, PSW3. Okay, so we can say when the three pressure switch are turned on, all of the three are turned on, then my C1 will turn on, and that will make the first condition become true. Right? Then I program second condition. Second condition is my C2. Condition 2. Okay, so condition 2, according to the original requirement, is only 2 out of 3 door switches. There are three switches, LS2, LS1, LS2, LS3. Right? When only 2 of them are closed, then these conditions are met. So what I can do is, okay, for this one, there are different approaches. One approach, you need 2, right? So I will just say if two of them is met, then this one will be okay. But there are only 2, right? There is only 2. Only 2 would have different combinations. You have LS1, LS2, and the LS3. Actually, if you want to, one easy way is just, this is my LS1, this is my LS2. Okay, if these two okay, then my condition 2 would be alright. But if I have LS1 and LS3, it's also okay, right? So this is another possibility. So if you have more than one possibilities, we can parallel them, right? If you have LS2 and LS3, also can, right? Only 2 right? Only 2 switch turn on, it will make this condition become true. So we can do something like this, okay? So we can exhaust all the conditions, all the possibilities. So these are all the possibilities, either 1 and 2, 1 and 3, or 2 and 3, right? No more other combinations. So all these, we see only 2 out of the 3, these are the possibilities. So all these possibilities will make condition 2 true, right? So the condition 2 now become, this is also programmed. Okay, condition 3. So well, we can do condition 3. All right, condition 3 is C3 here. C3 is linked to our reset switch. It says reset switch must not be closed, right? Must not be closed. So how do we meet that condition? We can. This is our C3. Reset switch. Reset switch is called what? Reset switch is called just reset switch. Okay. All right. So the reset switch, if I do like this, is it okay? So if I do a reset switch, so when the reset switch on, C3 will be on, which is wrong, right? Because we need the reset switch not to activate. Okay, not to activate. That means the reset switch must not on in order for the condition 3 to be true. Right? It says here, reset switch must not close. Right? Must not be closed. The reset switch is also normally open switch. So how do we meet this condition? Not closed. Not closed, we can do this lah. Okay, we can do a normally closed reset switch here. So in this way, the condition 3 will met if the switch did not activate, right? If you didn't touch the reset switch, okay, it would turn on the condition 3, right? Because it's normally closed. So this will make our program complete, okay? So for this example, we have three conditions given to us. Okay, we have three conditions. So what the approach is to, okay, imagine I just put three conditions, represent the three conditions by three memory global memory bit, C1, C2, C3. Okay, and when they all met, my green LED will turn on. And then subsequently, I program the three conditions. This actually is a preferred method, okay, for ladder diagram programming, because this way is clearer. Whenever people look at your program, they will now quite clear on how you did it, right? They will know, oh, you have three conditions, and this is the way you get it done. But of course, not every problem can be so straightforward, so that the conditions are so clearly spelled, like just 1, 2, 3 conditions, then you produce output, right? Sometimes the conditions are more complex. They have interlocking, one affecting another, and so on. So we'll gradually learn the other techniques as we go along, okay? For this problem, now some of you may be thinking, right, can I just do it directly? You know, you have three conditions, I will just do it directly. Sometimes if you are clear, it's possible, okay? You can do this directly. You say, oh, the three switches must turn on. Okay, then you have the only two of the switches must turn on. Okay, and then the reset switch not turn on, and that will produce my green LED. Right? So can I just design like this? Yes, of course you can do it. All right. So maybe first intuitive is to design in this way, okay? So these are the switches, the pressure switch 1, 2, 3, right? These are the LS1, LS2, LS1, LS3, LS2, LS3. This is our reset switch. Okay, of course you can program directly like this. For this particular problem, these are still okay, still clear enough for people to understand. Okay, but what I'm saying is the initial approach that I had is actually a better approach where the program is clearer. Okay, so people can follow you quite clearly. Now, for this approach that we put all the logical conditions into one line, sometimes it becomes complex. Okay, sometimes people have problem follow this. Okay, especially if it's not so straightforward, that's 1, 2, 3 conditions. And if there are some interactions, have to one part affecting another part, all right? For example, this part, if we somehow also affect this part, then the logic become quite difficult to follow, right? Then the program is become difficult to follow as well. So in PLC, we do have a guideline. We should try to make our PLC program easy to follow, others easy to know what you are doing. So we are recommended not to have very complicated logic in one line. That means put everything in one line to try to accomplish all the operations in one line. Rather, we are recommended to have simple logic each line, easy to follow logic. People when see this line, they can understand what you are trying to do. But you can have more lines that are easy to follow. That one is still easier to understand than if you put a lot complex logic into one line. All right. So just share with you on some of these philosophies now. Okay. All right. So this is our tutorial question here. We do have some more, but I think we don't have time. Okay. So we'll stop here. Not sure whether you have any questions for me. Hello, class. If okay, then I will capture the attendance here in this manner. Okay, these are the attendance. Right now I have 19 of you. Sorry, 18 of you here. Anyone are not in the list because just now I saw we have one time I have 20 participants, excluding me. That will be 19 of you, okay. But right now I only have 19 of you here. So I will be, that means one somehow not around here, okay. Some cannot join. Okay, actually, are you all here, or 21 of you all here? May I know whether all 21 of you are here? Yeah. So yeah, I saw your message. Do we have anybody not turn up today? Do you recognize?
Everyone here.
Huh?
Everyone is here.
Everyone here. Okay, there are 21 of you. Okay, so yeah, I will stop here. But I need to discuss with you one thing. Have you decided on your class rep and the assistant class rep? So this one I need to report to school. So any decisions on your class rep and you able to see my list here? Can you tell me who is a class rep?
Class rep who? Yes, sir. Yes. I. Ask who is the class rep lah?
Huh?
Yeah. Wait. You want to take over another year, man? Huh? You want to take another semester, man? I don't mind. Or whatever.
16.
Umara?
I don't want cover. I don't want.
Huh?
Super gaming.
Who is class rep can decide or not?
So, Cho, your question is who's going to be the next class rep, right?
Yes.
You want? Brian, you want to be a?
I think half a day already.
Huh?
Brian Lee wants to be class rep.
If I become right, then Brian will become an assistant.
Sure, Brian. Shut up. Brian Lee wants to become the class rep.
16.
Brian
16.
Brian
V. 16, 16,
6. Oh, here. Oh, okay. We have two Brian here.
Yeah.
Okay.
And assistant is Brian Ang.
No. My assistant, number 5.
Assistant. Oh.
Number 5.
5.
Assistant is number 5.
Right. Okay. Assistant.
He's angry already. He angry already.
Can we decide this one? I can report to school this one.
Wait, should I ask the assistant because he
No,
cannot
no,
sign.
no, no, no. He pushed me now, the water one.
Sure, can, sure.
Yeah,
Huh?
sure, can.
Really? Okay. You must say so, huh? Okay.
Sure, your attendance take already, right?
I just captured, but you see everybody here, right?
Yeah, everyone here.
Everybody here, then I'll just take everybody lah. But I
Wait, I
still,
check account.
I still do a capture here. This one, 19 of you in here.
Yeah, sure, 21.
21 now. Okay, then everybody around now. Okay.
Yeah.
Okay, then this is Brian Wee will be the class rep. Okay, try to be.
Yay! Yay!
You two will help me, okay? For this semester, okay, I'll have duties for you soon. All right, okay, I think that we'll forgo the exit poll lah. No time already. Your next your next lecture are probably offsite already, right? Yeah. Okay then. Bye bye then.
Bye bye.
Okay. Bye bye. Bye bye.